conditioning. Air conditioning is referred to the not only cooling, sometimes it also refers to the heating also. Air conditioning refers conditioning of air. Conditioning of air means it's not just only cooling. Uh, Sometimes it may be heating also. In addition to that, we have to maintain the other parameters, namely humidity for our comfort, for the human comfort. So now let us understand how far that human comfort depends on this humidity and all. For example, if the refrigeration, if you see our refrigerator, domestic refrigerator, or our split AC, whatever you take, so we call it as a refrigeration. But in air conditioning, in addition to that, your cooling effect, sometimes a comfort condition maybe a heating also. How, for example, in our country, it is you see that it is always most of the time in an year, especially in our places and all, it is very hot. So that we always prefer low temperature in our particular space, whether it is the office or room, whatever you call. But if you see about in other places, suppose in other countries, the Western countries and all, you see that outside may be sometimes cold. Maybe it may go up to 5 degrees Celsius, 2 degree or 3 degrees Celsius, even in our country also in some places. So during the time, we won't prefer to have the lower temperature in our room or office, whatever it may be. So we need a warm air. Right? So in that case, we need to heat the air and we have to attain a required comfort condition, maybe the temperature of some around 20 degrees Celsius or 18 degrees Celsius. And outside temperature is very much lower. So that task cannot be achieved by a refrigeration equipment. That task can be achieved by a air conditioning equipment. Okay, air conditioner is different. Refrigerating equipment is different. Whatever we use nowadays in our home and all, only refrigerating equipment. So it can give only cooling effect here. In addition to that, heating, we need to understand another terminology called humidity. What is humidity? Humidity is nothing but amount of moisture content present in the air. Sometimes we might have seen in our suppose if you are watching our cricket or sports, some other sports and all. So when they are giving the temperature of that particular place, they might have specified relative humidity (RH). They will specify it as 50%, 60%, 70% like that. So what is the meaning of that relative humidity? It represents more the relative humidity, more the value of the relative humidity. For example, if the relative humidity is 80 or 90 means, so more moisture content is present in the air. Uh, there is fed up with more moisture, and relative humidity is 100% means completely air is saturated with the water. That is water vapor in the supersaturated state. If the relative humidity is low means the air is no moisture. Means moisture is very less, 10%, 20%. Like exactly which relative humidity will be giving us the uh, comfort, whether it is a low humidity or a high humidity. Any answer from you? Humidity the relative humidity irukkalama. So edu namakku comfort ah irukum, human comfort, whether it is low humidity or high humidity.
Low humidity then sir.
Low humidity இல்ல மூணு எடுத்துக்கலாம் நம்ம. Low, moderate, high. இதுல எது நம்ம comfort? Any low humidity.
கார்ல மாய்ஸ்டர் அதிகமா இருக்குன்னா நமக்கு இதா தானே சார் இருக்கும். ஏர்ல மாய்ஸ்சரைஸ் அதிகமா இருந்துச்சுன்னா நமக்கு இதா அன்கம்ஃபர்டபுளா தானே இருக்கும்.
Correct. Moisture content is very high means it is uncomfortable. but moisture content is very low means that is also uncomfortable. எப்படின்னா we always prefer moderate humidity. Even an air conditioner it will maintain a moderate humidity of 40 to some 55-60% only. So let us understand the reason also. For example, let us take a high humidity place. For example, we take two places in our state. Okay, we take it as Chennai. Take it another place like our Coimbatore and all. Okay, so you see that temperature here in Chennai, for example, it is 40 degrees Celsius. Otherwise, not 40. Okay, let us take some 35 degrees Celsius. Okay, the same 35 degrees Celsius temperature will assume it in Coimbatore also for a particular day. Okay, so temperature is same. Okay, so where you will be feeling comfort in Chennai or Coimbatore? Obviously, our answer will be in Coimbatore only. Correct, Amma?
கோயம்புத்தூர் சார்.
Yes. என்ன ரீசன்? பிகாஸ் டெம்பரேச்சர் சேமா இருக்கு, பட் அங்கதான் கம்ஃபர்ட்டா இருக்கு. என்ன ரீசன்?
கூலிங்கா இருக்கு சார்.
கூலிங். இல்லம்மா, நம்ம வந்து இப்போ we are talking about only டெம்பரேச்சர் மட்டும் தான் நம்ம சொல்றோம் இல்லையா? ஸோ டெம்பரேச்சர் வந்து ரெண்டு இடத்துல சேமா கூட இருக்கும், பட் என்ன சென்னையில வந்து we feel uncomfortable. என்ன ரீசன்? என்னன்னா எஸ், பிகாஸ் இட் இஸ் a coastal area இல்லையா? சென்னை இஸ் coastal area. So you see that during summer the temperature is increases, so more water will evaporate from the sea. Okay, so when the water is evaporating, it is in the superheated state, it will mix with the air. So air will be added with the more moisture. So when there is a more moisture, suppose for example relative humidity is 90 or 95%. So see, we all know that sweating is taking place in our body to maintain our body temperature. So when the temperature is increasing, sweating, so what is happening? So the water particles from our body will evaporate, and then it will go to the air. Already all air is saturated with the water molecules. So the water coming out from our body that will not evaporate. So we'll be feeling uncomfortable, right? So when the humidity is very high, the water evaporation from our body during sweating will be very less, so that we'll be feeling uncomfortable. That is one point. So that high humidity is uncomfortable, as you said. Okay, coming to that low humidity, very low means the air will be so dry. The air will be so dry means, so it is a 10% or 15%, 20% means, in that case also will not be feeling uncomfortable, because the dry air is coming, and if dry air is surrounded by us, again we will be feeling uncomfortable. Like our desert area, desert is completely relative humidity is zero. Desert, there is no water. So if you see that, even if a slight rise in temperature, okay, so the dry air will be this surrounding will be the dry air surrounded by us will be making more uncomfortable. So in that case, so a moderate humidity of around 40 to 50-55% is highly desirable for a comfort. So any air conditioner, okay, will be operated to maintain the moderate humidity. Okay, that is one thing. So this is all about your air conditioning part. So now the basic the difference between refrigeration and air conditioning is, refrigeration is always with respect to the cooling. No heating will come here. Air conditioning, both heating and cooling, and also the maintaining the comfort condition. So in that way we can understand that this refrigeration and air conditioning. Now we'll get into this. Now we'll see the refrigeration part now. After that we'll pass on to the air conditioning part. So this is the definition that we are given here. So whatever we have discussed, the same thing. It's defined as a process by which a temperature of a given space is lowered below the atmosphere or surroundings. So the lower temperature is always called as a refrigeration. So basically these are all the applications for the comfort conditions for the industries, even for preservation of medicines or food products, even for the rocket fuels and all, because we have a low temperature, we need to maintain some of the rocket fuels. For that we need to maintain low temperature, isn't it? We call it as a cryogenic. Cryogenic is again, it is dealing with the low temperature. Cryogenic fuels, so that is completely related to the rocket fuels and computer functioning also. You see that we always prefer our laptop or system to be in a cold place, an AC room. It will because it will not be heated up. It can very effectively work it. Suppose if it is very hot, so even we may feel that the functioning of computer or laptop may be lagging, so that we might have felt. So in that way, the refrigeration, the cooling process finds application in all those places. This is very vital. Okay. Now we have some technologies related to the refrigeration. One is we call it as a COP. COP is referred to the coefficient of performance. So we might have studied in our thermal engineering one also. It is nothing but COP is nothing but it is nothing but an efficiency. Suppose for if we take a heat engine, we call it as a thermal efficiency. Just similar to that, it is an efficiency of a refrigerating machine. So how effectively it works. So what is the definition of that COP? It is nothing but it is the ratio between the refrigerating effect by work input. Refrigerating effect means what is the cooling effect we are getting. The numerator will have a refrigerating effect, and the denominator work input, because we have to, for a refrigerator, refrigerating machine and all, compressor is that compressor gets power input. We need to give the power input, so that always it requires some input for refrigerating machine to work. Because according to our second law of thermodynamics, always heat may be flowing from high temperature to low temperature naturally. But if we want to transfer the heat from low temperature to high temperature, so we need to give work input. So transferring of heat from low temperature to high temperature is nothing but functioning of our refrigerator. So based on that law, for functioning of refrigerator, it needs some power input. That is the nothing but your compressor. Compressor gets power input. Okay. So more the power input, lesser the effectiveness, because denominator work input is the, so if the power input, if it consumes more power, so automatically your COP will be decreasing, because denominator is increasing, so COP may be decreasing. So in that sense, so we need to design a system so that it requires a minimum power input. It consumes minimum power, so that our COP, our effectiveness of the machine will be better. There is another terminology, we call it as a relative COP. This is nothing but comparing our actual and theoretical COP. What is actual and theoretical COP means? So a theoretical COP means by calculation, by analysis, we get some COP value, coefficient of like a efficiency value. So we'll get some efficiency or COP value. So because of some losses, our actual COP will be less than. So we'll compare that one. We'll get a relative COP. The thing is, again, the reason for having theoretical COP is without any loss, we can understand how much we are getting. With loss, how much we are getting. So how we can improve the actual system by comparing with the theoretical one. So we'll keep a theoretical COP as a benchmark or a reference. We'll improve our actual COP of a particular fish. So in that way, we used to find out the relative COP. Okay. So if you come to our lab and all, so we have the experimental setup for finding the COP of your refrigerating machine. Even in your diploma course also, you might have done vapor compression refrigeration system and all. I hope you would have done some experiment. Okay. Now, there is another terminology in our refrigeration. We call it as a ton of refrigeration. Okay. So, ton of refrigeration is nothing but it is a conventional term which comes from so what we have given it here. It is nothing but amount of uh, heat removed from the surroundings, which is equivalent to the heat required for melting of 1 ton of ice in 1 day. So from that reference, we call it as a ton of refrigeration. So that equivalent value is, in terms of our SI unit, it is 3.5 kilowatts. So whenever we go for buying AC and all, we used to call how many tons. The ton is nothing but a ton of refrigeration. We prefer 1 ton, 1.5 ton, 2 ton. That is nothing but your ton of refrigeration. How we achieved this 3.5 kilowatts? Okay, we have a small calculation. I'll show you. Okay, you see it here. Okay, ton of refrigeration. So the definition was amount of heat required for melting of 1 ton of ice in in a particular day. Okay, that is for 1 hour. you see that exactly for 1 ton of ice, it is precisely it is 907 kg. That only call it as a 1 ton. So we have another parameter called the latent heat of ice. What is latent heat of ice? It is nothing but amount of heat required to melt a ice from 0 degrees Celsius to uh, water at 0 degrees Celsius. இந்த ஐஸை மெல்ட் பண்ணுறதுக்கு ஐஸ் மெல்ட் ஆகும் இல்லாமல் அதுக்கு நம்ம எவ்வளோ ஹீட் கொடுத்தா அது மெல்ட் ஆகும். அந்த ஹீட் திஸ் இஸ் ஸ்டாண்டர்ட். We call it as a latent heat of ice. Latent heat means there will be a phase change, no change in temperature. That we call it as a latent heat. So for melting of ice, for this is the so much kg for 907 for 9000 for 900 kg of ice. So this much amount of heat has to be given for 1 kg of ice. 1 kg of ice we have to give this much amount of heat. For 900 kg I have to multiply this, correct? And then for 1 hour, that's for 1 day, isn't it? So what I have to do it, if I'm dividing by 24, I'll be getting for 1 hour, and I'll be getting in kilojoules per hour. I need it for in kilowatts. So hour, how do you convert hour into seconds? So I divide it by 3600. So if I am doing this calculation, so I'll be getting my for 1 ton of refrigeration. So my the corresponding equivalent value in kilowatts. This is our SI units. So I'm getting 3.516. So what is the meaning of this now? 1 ton, okay. What is the meaning of this? So it can enable, what is kilowatts? Kilojoules per second, correct? Kilojoules per second only, we call it as a kilowatts. So 1 ton means it can able to remove 3.5 kilojoules of heat per second. That system. If it is 2 tons, it can able to remove 7 kilojoules per second. So if the ton is increasing, the rate of heat removal will be more. Rate of heat removal is important. Rate, how fast the heat is extracted and it is sent out. Okay. So this is directly proportional to the capacity of the your AC. For example, if you take a split AC, we take a 1 ton AC, 2 ton AC. Okay. For example, in a 10 by 10 room, we fix some 1 ton AC. Okay. The same 10 by 10 room, adjacent to that room, we fix here. For example, you can fix a 2 ton AC. Okay. Assume that the room temperature is same. Initially, the room temperature is the same. Some 35 degrees Celsius is there. Okay. So we have set the temperature in our remote to reach the temperature of some 20 degrees Celsius, 35 to 20 degrees Celsius. Okay. So one room is having 1 ton, another room is having 2 ton with the same space, 10 by 10 room. Okay. So which room will get faster cooling? Which room will reach the 20 degrees Celsius faster? Obviously, 2 tons. Correct, Amma?
Yes, sir.
2 tons. 2 tons. என்ன ரீசன் அப்படின்னா ரேட் ஆஃப் ஹீட் ரிமூவல் இஸ் திஸ் இஸ் 3.5. இந்த ரூம்ல 3.5 kilojoules per second ஹீட்டை ரிமூவ் பண்ணி வெளியே அனுப்புது. அனதர் ரூம்ல 7 kilojoules per second ஹீட்டை ரிமூவ் பண்ணி வெளியே அனுப்புது. ஸோ ரேட் ஆஃப் ஹீட் ரிமூவல் இஸ் ஃபாஸ்டர் இன் the 2 tons AC. So quickly it will reduce the temperature. It will come down. So that is the advantage of a higher capacity tons AC means. So the cooling effect will reach fastly. But what is the disadvantage? என்ன drawback-மா? அதுல என்ன drawback இருக்கு? From our
Power
side.
consume அதிகமா இருக்கு.
Very good. அவ்வளவுதான். Our consumption is more. So it can able to extract more heat. Cooling effect fast வந்துரும். But it consume more power. So if you are ready to pay for the more power consumption, then we can accept it. So in this way, we can understand the ton of refrigeration, the relation between our ton of refrigeration and capacity of the refrigerator. So I hope you are clear with this ton of refrigeration. Okay. So more the ton of refrigeration, the heat extraction rate is faster. So that particular space will reach the cooling fastly, but it consumes significant amount of power. So in that way, we can understand the ton of refrigeration. So I hope you understood. Okay. And then there are two types of refrigeration systems is available. Normally we use it. One is a vapor compression refrigeration system. Another one is the vapor absorption refrigeration system. So already you may have some idea about this. Anyway, we are going to see in detail about this vapor compression and vapor absorption system, where we'll use this. What is the basic difference between this? Okay. Now, if you see our vapor compression system, normally all our domestic refrigerator, our refrigeration system we use in our vehicles, our split AC, all is working on the vapor compressor refrigeration system. It consists of mainly four prime components. One is compressor, condenser, expansion valve or throttle valve, and the evaporator. These are all the four prime components without which the system will not work. In addition to that, we may have other components also, that is an auxiliary equipments. But without these four components, the system will not work. Compressor, condenser, expansion valve, and evaporator. So now let us understand uh, how the system is working. So you may have some idea, but we will understand with some theoretical concept and also with our thermodynamic problems also. So any vapor compression refrigeration system will consist of a refrigerant. Namely, colloquially we call it as a gas. A refrigerant. We have refrigerant of various kinds. Uh, we call it as the R12, R22 refrigerant commercial names. Okay, R134A, ammonia, like that. We have various refrigerants are available. The refrigerant will undergo a various processes in all these four components. So it is a cyclic process. So I can start anywhere. We can because I can end anywhere here. Being a cyclic process, completely closed system. Now normally we cannot be able to see that in any refrigerator or any refrigeration system. So uh, it will be at the rear, or it will be hidden. So we cannot be able to see it. So exactly what is happening. So in the evaporator, your refrigerant will be come out in the hot condition. So evaporator is nothing but your freezer box. In our refrigerator, if you take our freezer box, that is nothing but an evaporator. So the refrigerant, it is a closed system. The refrigerant will come out in the vapor form. The hot vapor refrigerant will enter into the compressor here. So the compressor will further increase its pressure and temperature. So the pressure and temperature of the refrigerant is increasing. Okay, so it is in the vapor form only. So that refrigerant, the high pressure, high temperature refrigerant is entering into the condenser here. We use some external cooling arrangement. If it is a large capacity refrigerator, we need to use a fan and all. If it is a small capacity refrigerator, no need atmospheric that air is just sufficient to cool it. Okay. So the hot refrigerant, which is at high pressure and temperature, which will be enter into the condenser. Condenser is nothing but a heat exchanger. You will have a number of tubes. We might have seen just like a tube. You bend your tube in the rear of a refrigerator or a tube mari பார்த்திருக்கோம். So that is our condenser. Air side la பார்த்திருக்கோம். ஒரு grill மாதிரி இருக்கும். That is our condenser through which refrigerant is flowing. So here the vapor refrigerant is converted into a liquid refrigerant because we extract heat from that refrigerant. So there will be phase change here. So during that phase change, since the phase change is taking place, almost the temperature, theoretically the temperature remains constant. Okay, if it is in the superheated state, we'll reduce it to the saturated state. After that, the phase change will be taking place. So in the outlet of the condenser, you have a cold refrigerant will be coming. I mean, the refrigerant which is in the liquid form will be coming out here. Not a cold refrigerant, a warm refrigerant only. Refrigerant in the liquid form. It is vapor form. Here it is in the liquid form. It will enter into a expansion valve. Expansion valve is we also call it as a throttle valve. Exactly what is throttle or expansion valve means? It is a very restricted passage. For example, if you take already we have discussed one day this one. So if we take a restricted passage, assume that our tap, our water tap is close to almost 90%. You have closed the water tap. We have a small space, a small opening. If I am having a small opening, if I am allowing this uh, that liquid refrigerant to pass through this, so it will be uh, coming through a very restricted, a small passage. That is very small diameter tube will be there. So in that way, we can assume uh, our expansion valve or throttle valve here. So when it comes through a restricted passage, there will be huge pressure drop. So always there will be already the pressure has increased here. So it is a high pressure refrigerant, the liquid form which is coming through this. So when it comes through a restricted passage, very small, very small diameter, maybe 1 mm, 2 mm, 2.5 mm like that. So when it passes through this, so there will be huge pressure drop. So because of this huge pressure drop, immediately there will be a temperature drop will be there because pressure and temperatures are directly proportional. So because of that, there will be a huge temperature drop. So immediately we'll get a cooling effect here. Even if we just feel it here, it will be so cold. The reason there is a drop in pressure and corresponding temperature will be there. So here only we are getting a refrigerating effect. So the cold refrigerant, the liquid form which will enter into the evaporator, your freezer box. If you closely observe our freezer box, so you might have seen, yeah, just like a tubes surrounded in the freezer box inside this, some hollow tubes, a square shape or rectangle shape, you might have seen. So through this, our cold refrigerant in the liquid form will be flowing. So whatever the load we keep it inside, so that is hot because it is a cold refrigerant. For this, it is hot. Maybe even in atmospheric temperature, it is hot only. So when it flows through this, so there is a temperature difference between the that load and then this refrigerant. Refrigerant maybe even sometimes -2 or -3 degrees Celsius, even -5 degrees Celsius also. Okay. So here the load may be at 30 degrees Celsius or 35 degrees Celsius. So the temperature difference is very high. So immediately the refrigerant will absorb heat from this. So immediately, so it gives a cooling effect. So when the refrigerant is absorbing heat from that, the refrigerant vapor will be converted into a liquid because there is a phase change here. There is a phase change here. That's why we call it as a evaporator. So the refrigerant, the liquid form, will be converted into a vapor form when it absorbs heat from the load. So the vapor refrigerant again will enter into the compressor here. So here when we start here, we call it as a vapor refrigerant. Again, we end here as a vapor refrigerant here. So in this way, our vapor compression refrigeration system is working to achieve the cooling effect here. The same process we have represented in our pressure enthalpy diagram and a temperature entropy diagram. So the 1 to 2 process, we call it as a isentropic compression, which is taking place in the compressor here. So always that compression expansion process, we call it as isentropy. Entropy remains constant. We observe our pressure enthalpy and TS diagram here. So 1 to 2. So temperature is increasing, pressure is increasing, correct? So it is rising. 1 to 2, pressure and temperature is increasing. And the entropy remains constant, vertical line, so entropy remains constant. Its enthalpy is also increasing here. Coming to our 2-3 process, our 2-3 process, if you see it here, the pressure remains constant. Right? Actually, there will be some pressure drop will be there practically, but theoretically, we'll assume it as some pressure remains constant here. So here, the temperature is also remain constant when the phase changes occurs. But if you see it here, 2 to 3, that here the temperature is drop is taking place. After that, temperature remains constant. The reason is this is our saturation line, like our Molar chart, HS diagram. This is superheated state. This is superheated state, and this is saturated state. This is nothing but wet condition. So always our refrigerant will be in the superheated state after coming out of the compressor here. So we have to cool it from superheated state to the saturated state here. Once it comes to the saturated state, after that, if we cool it further, so it will be converted into a wet region and liquid region here. That's why here the temperature is decreasing. After that, phase change is taking place. The temperature remains constant. So in this way, we can understand our 2-3 process. So 2-3 process, we call it as a constant pressure heat rejection. After entering into the expansion wall, so what is happening? So we understood that there is a huge pressure drop, so that we can see it here. The pressure is dropping vertically downwards. So there is a huge pressure drop here. When there is a pressure drop, corresponding temperature drop will also be there. So it is coming vertically downwards here. During this process, we assume it as enthalpy remains constant, but there will be a small change in enthalpy. Theoretically, we assume it as enthalpy constant. So that's why you get a vertical line is vertical here. The entropy is constant. This is vertical. The enthalpy is constant. This is vertical here. Coming to our evaporator 4-1 process, this is also heat transfer process. Okay, always the heat transfer process is constant pressure. Either it is a heating or cooling. This is nothing but your heat transfer process. That is 2-3 and 4-1 here. So in the 4-1 process, what is happening? It is a heat transfer process. It is absorbing heat from the load here. During this process, again the pressure remains constant as well as the temperature is also constant because the phase change is taking place. Whenever a system undergoes a phase change, there won't be any change in temperature. So in this way, we can understand the thermodynamic process of vapor compression refrigeration system. So the 1 to 2 process represent in the compressor, 2 to 3 process representing in the condenser, the 3 to 4 process is represented in the expansion valve, and 4 to 1 process which is represented in the evaporator. Because we need to conversant with this, because we need to solve problems on vapor compression system. So for that, the condition of refrigerant will be given. So we should know how to represent all those things, and also we should know the thermodynamic process. Accordingly, we'll have to solve the problems. Okay. For that only, so we have seen in detail this pH diagram and TS diagram here. This is all about your vapor compression refrigeration system here. Now, in the vapor compression refrigeration system, we have another the effect called superheating and subcooling. Superheating and subcooling here. So what is the meaning of superheating and subcooling here? Now I am coming back to our original system here. So if you see it here, this is our saturation line, this is our superheated region, this is our wet region here. Generally, what will happen in practical case, when the refrigerant, this is in the liquid form, when it comes out here, it is in the vapor form here. So the refrigerant in the vapor form will be entering into the compressor. So we cannot expect if it is a normal functioning of vapor compression system. If this is the system, means what will happen? Sometimes the refrigerant may not be heated to a sufficient level, so it may not be a dry or superheated state. Some moisture may be present in that. So that means, so the refrigerant may be entering from this point itself. In the region lay on the refrigerant enter in the region common. There may be a possibility practically. So if this is the case, then what will happen? It will spoil the compressor. So no moisture or water droplets or moisture content should enter into the compressor. If it goes, so it may affect the performance or the malfunctioning of compressor may take place. Water droplets will go, so compressor function will not be proper, so it may affect the performance of the compressor there. And then we have to ensure that at the outlet of the compressor it should be superheated state. Okay, so we cannot expect in the normal functioning, we cannot expect a superheated state, dry saturated compressor. If this is the case here, then we'll have a problem. It may enter in the wet region. So for that, we have to ensure that always dry or superheated state is achieved at the outlet of the evaporator, and superheated state is achieved at the outlet of the compressor. This is superheated state, but practically, it is not possible sometimes. So we may get a dry saturated. Inge point 1 reach the 2. So this is dry saturated state and below dry saturated state wet region. So in the cases, so the moisture present and then performance will be lowering it. For that, what we'll do it, we have to ensure that if you forget about this heat exchanger, you take our compressor, condenser, expansion valve and evaporator, a normal, which we have seen in our previous case, compressor, condenser, expansion valve and evaporator. So what we do it here, we do a superheating and subcooling process. Okay, so that we have to ensure that at the outlet of the evaporator, okay, this is our what is the point here outlet of the evaporator? 6 point. Okay, when it comes out here, we further heat it, so it is coming to the superheated state, the region on the superheated region. So we ensure that it is in the superheated state. Entry of the compressor here. If entry itself superheated means after compressing, definitely pressure and temperature will increase. Definitely this will be in the superheated state only too. So we'll ensure that. Okay, this is one point which is with respect to the superheating. Now coming to the subcooling. So what is subcooling now? So here again I am coming back to our standard refrigeration system. Here it is a condenser here. So we have seen that at the outlet of the condenser, all the your vapor is converted into liquid. So a 2 to 3 process. When it comes here, it is saturated liquid state 0.3. இருக்கலாமா critical point, saturated liquid, இங்க வந்து saturated vapor line. So it has to reach the 0.3 here. Suppose if 0.3 இங்க கூட இருக்கலாம், இந்த பாயிண்ட்ல என்டர் ஆகும் expansion valve. அப்படின்னா என்னதுன்னா all the refrigerant is not converted completely into liquid. Some refrigerant in the vapor formல இங்க என்டர் ஆகலாம் இந்த மாதிரி இருந்ததுன்னா. So it is ideal. அப்போ 0.3 இங்க இருந்ததுன்னா it is in the wet region. இது some refrigerant in the vapor form may also enter and combine with the liquid form. Liquidல வந்து some vapor mix ஆயிருக்கலாம். So if that is the case, what is the effect? What will happen means here the flow will be obstructed. It is completely liquid means the flow may be there. It is a restricted passage. The vapor may clog the path, and also there is a phenomenon called vapor starvation. There may be or tuck no sound கேக்குமா in the expansion valve. So that is due to the refrigerant which is entering into the expansion valve. A combined vapor liquid refrigerant அந்த மாதிரி போச்சுனா பியூரா லிக்விடா இல்லாம வேப்பரும் மிக்ஸ் ஆகி போச்சுனா you get a sound as tuck ன்னு ஒரு sound கேக்கும். Okay, so that we call it as a vapor starvation. The flow obstruct ஆகும் அந்த இடத்துல. So the expansion valve will not function properly, will not get a proper expansion here. That expansion proper நடக்காது. So that the COP will be reduced.
Sir, voice கேக்கல சார், பிரேக் ஆகுது.
அப்படியா? ஒரு minute, I'll change the network. Signal கம்மியா இருக்கு. Network change பண்ணிக்கிறேன். Okay, ma'am. So we have to ensure at the outlet of the condenser, we need to have a pure liquid which is entering into the expansion valve. For achieving these two, we need to do the two processes called superheating and subcooling. So superheating is to ensure that, I repeat again, superheating is to ensure that vapor is completely dry when it is entering into the compressor as well as when it comes out through the compressor. Compressor குள்ள போகும்போதும் compressor குள்ள வெளிய வரும்போதும் vapor will be your refrigerant will be pure vapor. அந்த கண்டிஷனுக்காக we do superheating. Subcooling is okay, our refrigerant will be in the liquid form when it enters into the expansion valve. Expansion valve குள்ள போகும்போது pure liquid இருக்கணும். Mixed liquid and vapor refrigerant இருக்க கூடாது. So அந்த மாதிரி கேஸ்க்காக we use subcooling. Okay. So this too should be ensured while designing a actual refrigeration system. For that, there will be a slight modification in the existing system of vapor compression system. So that we'll provide a small heat transfer device, heat exchanger device. We'll use it. So now let us see that how it works. The usual way, your refrigerant will be coming out from the evaporator. Okay, so it passes through a small heat exchanger here. So if you see it here, there is another way. Refrigerant is coming out from the condenser. It will be very hot here. Correct? இந்த இடத்துல condenser வெளியில வரும்போது refrigerant actually it is vapor. It is converted into a cold. I mean vapor refrigerant is converted into liquid refrigerant. But எப்படி இருக்கும்? Same hotness இருக்கும். Hotness குறைஞ்சிருக்காது. ஏன்னா phase change தான் நடந்திருக்கு. அப்போ a hot liquid refrigerant is coming here. Okay. Here a vapor refrigerant is passing. அப்போ இங்க வந்து a hot refrigerant, இங்க வந்து cold refrigerant. So heat transfer will be taking place. அப்ப என்ன ஆகும்? இதுல இருக்கிற heat will extract, will heat this. When it gives this heat, this is this will become cold. So mutual heat transfer is taking place in the place like what we did it here. The refrigerant which is coming out from the evaporator should be heated. That's our concept. So அப்ப heat ஆகும்போது it will become vapor. The refrigerant which is coming out from the condenser should be further cooled so that there should not be any vapor. So it should be completely liquid form. So both will be combined in a heat transfer device here. Small heat exchanger மாதிரி இருக்கும். So இங்க heat exchange is taking place. So your refrigerant is giving its heat here, so it is cooled. When it gives heat here, it gets heated. So that this 6-1 process heated, we call it as a superheating process, and 3-4 process, it is cooling is taking place. So that we call it as a cooling process. We call it as a subcooling. Subcooling means so we are already here it is cooled, further it is cooled down. That's why we call it as a subcooling. Already it is heated here. Again further we heating it. That's why we call it superheating. So in this way, by using a small heat exchange, yes.
அந்த 3 to 4 இருக்குல்ல, அது இந்த 6 to 1ல இருந்து ஹீட் எடுத்துக்கிடாது சார்.
6 to 1ல இருந்தாமா?
6 to
ஆமா. இல்ல 6 to 1ல என்ன 6 to 1ல என்ன எப்படி இருக்கும்னா ரெண்டுக்குள்ள டெம்பரேச்சர் இது வந்து ஹாட்டா இருக்கும் இங்க இருந்து வெளிய வரும்போது. ஏனா ஆல்ரெடி
எவாபரேட் ஆயி தான சார் வருது.
இஸ் எக்ஸ்ட்ராக்டிங் ஹீட் எவாபரேட் ஆகாம வருது. இது வந்து வேப்பர்ல வருது இல்ல. இது வந்து எப்படி இருக்குன்னா இந்த இடத்துல வந்து ஹாட்டா இருக்கும்.
ஆமா சார், ஹீட்டா தான் இருக்கு. அதுக்கு
இந்த இடத்துல ஹாட் தான உள்ள. இந்த இடத்துல ஹாட்ல
தான சார் கண்டென்சரோட அவுட் இருக்கு. எல்லாம்
கண்டென்சர் அவுட்லெட். ஓகே, இந்த பாயிண்ட்ல தான் நம்ம சொல்றீங்க.
இல்ல சார்,
இந்த பாயிண்ட்ல தான சொல்றீங்க. இங்க இருந்து ஹீட்டா இங்க இருந்து
செக்ஷன் லைன் இருக்குல சார். செக்ஷன் லைன் ஹீட் எக்ஸ்சேஞ்சர்னு இருக்குல.
செக்ஷன் லைன் எந்த செக்ஷன்? ஆமா,
இதுல
இந்த இடத்துல தான் நம்ம சொல்றீங்க.
ஆமா சார்.
உள்ளேயா வெளியிலயா?
இப்போ 3 to 4
இருக்கு. உள்ளேயா வெளியிலயா?
3 to 4 லைன் இருக்குல்ல, எக்ஸ்பென்ஷன் வால்வுக்கு பதிலா அந்த லைனும் 6 to 1, அதாவது கம்ப்ரஸருக்கு போற லைனும் நியர்ல தானே இருக்கு. அப்போ எவாபரேட்ல இருந்து வர்ற அந்த நியர்ல தான் இருக்கு. அப்படிங்கிற பட்சத்துல கண்டென்சர்ல இருந்து ஆல்ரெடி ஹீட் ரெடியூஸ் ஆகி தான் வருது. இந்த எவாபரேட்ல இருக்க கொஞ்சம் ஹீட் ஆகி தானே அந்த இது வேப்பர் வருது. அப்படிங்கிற பட்சத்துல அந்த கூலிங் இது லிக்விட் வந்து இந்த ஹீட்டை வந்து எடுத்துக்கிடும்ல.
அந்த கண்டென்சர்ல வந்து என்ன ஆகும்னா இங்க வந்து கூலிங் அப்படின்னு சொல்லும்போது என்ன ஆகும்?
ஹீட் தானே சார் வெளிய
வேப்பர் வந்து லிக்விடா தான் கன்வெர்ட் ஆகும். ஓகே, டெம்பரேச்சர் வந்து கான்ஸ்டன்ட்.
கியூப் போகுதுல சார்,
ஹீட் தான் வெளிய போகுது. ஆனா என்ன ஆகும்னா இல்ல இங்க பாருங்க. ஆமா, இந்த இடத்துல இருக்கலாம். இங்க பாருங்க, இந்த இடத்துல இதான கண்டென்சர் ப்ராசஸ்.
ஓகே, கண்டென்சர் இருக்கு.
கண்டென்சர் ப்ராசஸ் இங்க வந்து சூப்பர் ஹீட்டர்ல சேச்சுரேட்டட் வந்து இந்த இடத்துல டெம்பரேச்சர் கான்ஸ்டன்டா இருக்கு இல்லையா? அப்ப என்ன ஆகும்னா இது வந்து நம்ம கூலிங் அப்படின்னு சொல்ல மாட்டோம். இந்த இடத்துல கண்டென்சர் வந்து கூலிங் அப்படின்னு
வாய்ஸ் பிரேக் ஆகுது.
கூலிங் சொல்ல மாட்டோம். வேப்பர் வந்து லிக்விடா கன்வெர்ட் பண்ணோம். இந்த ப்ராசஸ் இருக்குல்லமா, இங்க வந்து vapor refrigerant is converted into liquid refrigerant. அப்படிதான் நம்ம விட்டு கேக்குறோம். சிக்னல் கம்மியா இருக்குன்னு நினைக்கிறோம். கிளாரிட்டி இருக்கா?
ஓகே சார், இப்போ கிளாரிட்டி இருக்கு.
ஓகே ஓகே ஓகே. இங்க வந்து நம்ம என்ன நடக்கும்? ஆல்மோஸ்ட் தெர்மோடைனமிக்கலி இங்க வந்து டெம்பரேச்சர் கான்ஸ்டன்டா இருக்கும். இப்போ என்ன ஆகும்னா இது வந்து ஹாட்டா தான் இருக்கும் இந்த இடத்துல வரும்போது. ஓகே, என்ன டெம்பரேச்சர் இருக்கோ அதே டெம்பரேச்சர் நம்ம ஹீட்டை எடுக்கிறோம் அப்படின்னு சொல்றோம். அந்த ஹீட் வந்து என்ன ஆகும்னா அந்த வேப்பரை வந்து லிக்விடா கன்வெர்ட் பண்றதுக்கு தான் அந்த ஹீட்டை நம்ம எடுத்துக்கிறோம். நம்ம எடுக்கிற ஹீட் என்ன ஆகும்னா வேப்பரை வந்து லிக்விடா கன்வெர்ட் பண்றதுக்கு தான் அந்த ஹீட்டை நம்ம எடுத்துக்கிறோம். அப்போ ஃபார் எக்ஸாம்பிள் இப்போ நம்ம வாட்டரை ஹீட் பண்ற மாதிரி தான். ஓகே, இப்போ ஃபார் எக்ஸாம்பிள் இன்னொரு எக்ஸாம்பிள் சொல்றேன். ஐஸ் இருக்கு இல்லையா? ஐஸ் வந்து நீங்க வெளியில எடுத்து வைக்கிறீங்க. ஐஸ் வந்து வெளியில எடுத்து வைக்கிறீங்க. ஐஸ் வந்து ஃபர்ஸ்ட் என்ன ஆகும்? அது மெல்ட் ஆகி வாட்டரா கன்வெர்ட் ஆகும். ஐஸ் இஸ் ஃபேஸ் சேஞ்சஸ் டேக்கிங் பிளேஸ். அப்போ அந்த இடத்துல நம்ம கூலிங் சொல்றோம் இல்லையா? ஆனா ஐஸ்னுடைய டெம்பரேச்சர் வந்து இனிஷியலா 0 டிகிரி செல்சியஸ் இருக்கு இல்லையா? அது வாட்டரா கன்வெர்ட் ஆகிற வரைக்கும் 0வா தான் இருக்கும். நம்ம கூலிங் தான் சொல்றோம். ஓகே, ஐஸ் வந்து இப்போ எடுத்து நம்ம வெளியில வைக்கிறோம், ஒரு தட்டில் வைக்கிறோம் அப்படின்னா 0°C ஐஸ் இருக்குன்னு வச்சுக்கலாம் ஃபார் எக்ஸாம்பிள். அப்படின்னா அது ஐஸா
only
தான்
phase
இருக்கும்.
changes
அதை நான்
மட்டும்
கூல்
தானே
பண்றேன்
சார்?
அப்படின்னா வெளியில எடுத்து வச்சாலே கூல் ஆகும்.
only phase
ஃபேஸ்
changes.
சேஞ்ச் தான் வருது. ஃபேஸ் சேஞ்ச் அப்ப நம்ம ஐஸ் வந்து என்ன, ஆமா ஃபேஸ் சேஞ்சஸ் மட்டும் தான். ஐஸ் வந்து 0°C அப்படியே இருக்குன்னா அது நம்ம கூல் தான் பண்றோம். ஆனா என்ன ஆகும்னா மெஷர் பண்ணா அது 0°C தான் இருக்கும், ஆனா கூலா இருக்கும். அப்ப என்ன ஆகுதுன்னா ஃபேஸ் சேஞ்ச். அப்ப அதே மாதிரி தான் இங்க நடந்திருக்கு. அப்ப என்ன ஆகுதுன்னா டெம்பரேச்சர் வந்து இங்க கான்ஸ்டன்டா தான் இருக்கு. அப்போ ஸோ வாட் வில் டூ இட், அப்போ ஹை டெம்பரேச்சர் தான் இங்க உள்ள வருது. இங்க வந்து என்ன ஆகுதுன்னா ஸோ வி ஹாவ் திஸ், இந்த இடத்துல ஆல்ரெடி வி ஹாவ் இட் a temperature rise here. அப்ப temperature difference இருக்கனால so here the heat will be given here, so இது வந்து cool ஆயிடும். Okay, so that it will absorb heat, so it is coming to the vapor form, further dry saturated state கூட போய் superheated state கூட போலாம். அப்போ இது வந்து further heat ஆகுது, இங்க வந்து cool ஆகுது. So in this way we achieve cooling effect for the refrigerant which is entering into the expansion wall. We achieve heating when we enter into the compressor. So in the concept we call it as a subcooling and superheating. Okay, இது வந்து ஒரு இம்பார்ட்டன்ட் கான்செப்ட் மாதிரி. இது வந்து சம்டைம்ஸ் அனாலிசிஸ் கூட நம்ம இது யூஸ் பண்ணுவோம். பேசிக் லெவல்ல வந்து நம்ம பார்க்கும்போது இதுதான் அண்டர்ஸ்டாண்ட் பண்ணுவோம். பட் when we go for subcooling and superheating actual சிஸ்டத்துக்கு வந்து we have to understand this. A suction line heat exchanger, heat transfer device is provided so that both subcooling and superheating will be achieved by providing this. Okay, this is all about your vapor compression system. Is the time 7:24? Okay, so we'll go to the one more thing. Next, coming to the vapor absorption system. So vapor absorption system is completely different from our vapor compression system. First point, it does not have compressor. First, vapor absorption system will not have any compressor in that entire system. Other things will be common. You take a condenser will be that, expansion to that compressor will be replaced with the generator and absorber. Additional equipments and the generator and absorber. In the case of even steam is even hot water is just sufficient to run the entire system. We are going to see it now. How the hot water is just sufficient. Very small amount of heat is just sufficient. But in our vapor compression system, always we need electricity. If we don't have steam, we can go for electricity. But steam is also just sufficient the vapor absorption system. We are going to see the one system since it consumes a less amount of power. So it will be highly economical. That is the one point here. Okay. Okay, I think it is visible. Now, there is a big drawback in the vapor absorption system when compared to the vapor compression system. Your vapor compression system we can able to achieve a cooling effect very fastly. But in vapor absorption system, the cooling process is very naturally. It is having that problem we are going to see. Use vapor absorption system. The reason is it is having very very low COP. Your cooling effectiveness is very low.
So voice break ஆகுது, ஒன்றும் கேட்க மாட்டேங்குது. Hello.
Well, we take a 1 liter of water bottle,
ஒண்ணுமே கேட்கல,
keeping it in a refrigerator. in a freezer box. So it can be in one minute. Signal konja low. 1 minute. Okay. So in the case of a vapor absorption system, okay, Mama, clarity irka?
ஓகே சார், மறுபடியும்
Okay.
சொல்லிடுங்க சார், இதுக்கு முன்னாடி சொன்னது.
Okay, okay. So in the vapor absorption system, its cooling effectiveness is very, very low. Vapor compression system, for example, if I want to cool a water bottle, I'm just keeping it in my refrigerator, it may take 10 to 15 minutes, it may cool it. But in the vapor absorption system, it may take even 2 hours, 3 hours to cool down 1 liter of water. Okay, the reason is the cooling effectiveness is very low. So we'll see it, how the effectiveness is reducing here. For that, let us first understand this, the entire system of vapor absorption system. So it consists of evaporator, absorber, and major components: evaporator, absorber, generator, and condenser. So we use ammonia as the refrigerant here. We use ammonia as the refrigerant, and water will be the absorbent. Two fluids will be using. Two working fluids will be using. One is ammonia, another one is water here. We'll see why we use ammonia, what is the reason for that. Those things also we'll see it. Okay. So here, again, it is a cyclic process. Okay, so let us first take it in the outlet of our evaporator, because this is our freezer box. I'll start here so that I will end here. So the outlet of my evaporator, that is in my freezer box, our ammonia vapor will be coming out. Ammonia is in the vapor form, because ammonia will be liquid form, will be entering, it will be coming out as the ammonia vapor after absorbing heat from the evaporator here. Okay, so whatever the load you want to pull it, we'll keep it here. So ammonia vapor will be coming out, and then it will be entering into the so-called absorber. Inside the absorber, you'll have a water will be there. Okay. So the water, why we use this water and ammonia combination means water and ammonia will be having very good affinity. That means easily the water will absorb it, and the water will easily mix with the ammonia. That's why we use this water and ammonia. Okay, that mixture here. So when the ammonia vapor is entering, so here you will have a water here. So the ammonia will be readily absorbed by the water. So the ammonia and water mixture will be taken by a pump. We call it as more the ammonia means, we call it as a strong solution. Ammonia is less means, we call it as a weak solution. So the more ammonia, the ammonia rich heat exchanger here. In the heat exchanger, it will be preheated. Already we have here another line is that we'll see it later here. So it will be slightly preheated here. It enters into a generator. So when it goes to the generator here, so we'll supply a small amount of heat, either maybe a steam or a electricity. Electricity is just some 60 watts or 70 watts is sufficient. It is available in our lab. Okay, so if you see the capacity of amount of heat, electricity we give it just 60 watts, that equal to a small bulb, a very small amount of power. The reason is here we want to evaporate the ammonia. Okay, ammonia will quickly evaporate. The reason is ammonia boiling point is minus 30 degrees Celsius. If I'm just keeping it in my atmosphere, it can able to. If I'm giving a heat which will evaporate quickly, ammonia will evaporate, because having lower boiling point. Even a small amount of heat is just sufficient. A steam, a low pressure steam, hot water can able to evaporate the ammonia. So when the ammonia vapor is passing through this, because we are giving continuous heat supply here. So sometimes water
சார் ஒண்ணுமே கேட்கல சார். சார் ஒன்றும் கேட்கல.
Because of the continuous heat supply. When it reaches
மீதி எல்லாருக்கும் கேட்குதாப்பா?
boiling point. gets heated because of its low boiling point. கேக்குதாமா? clarity இருக்கா? ஓகே, கண்டினியூ பண்ணலாமா?
இல்ல சார், இதுக்கு முன்னாடி
கண்டினியூ
ஒண்ணுமே
பண்ணலாமா?
கேட்கல சார்.
அப்படியா? ஓகே
ஒண்ணுமே
ஓகே.
கேட்கல.
அதை வரமா ஒரு சிக்னல் வரும். பார்த்து ட்ரை ரீஸ்டார்ட் பண்ணி. Okay. Okay. So when this thing here, so we are giving a heat supply.
கேக்கு சார், ஆனா விட்டு விட்டு தான் சார் கேக்குது.
சிக்னல் இருக்கு. ஓகே ஓகே. சரிம்மா, இன்னொரு சரி ஓகே, இன்னொரு நெட்வொர்க் ட்ரை பண்ணலாம். ஓகே. So here the ammonia will be evaporated. So the ammonia vapor will be coming out. Some small traces of water vapor will also be there. And the water vapor வந்து actually it is undesirable. So we need to remove this water vapor. For that what we'll do it. இங்க வந்து நம்ம காமிக்கல. But in actual case, so this will be passed through edge. We'll allow the this ammonia vapor to pass through. அப்படி போகும்போது என்ன ஆகும்னா water will get condensed. Water condense ஆகி, so almost 90, 98, 99% pure ammonia will be passing through the condenser. The water particles separate பண்ணிடுவாங்க. எதனாலனா இங்க போகும்போது water அந்த freeze ஆயிடும். So ice form ஆயிடும். அதனால வந்து we don't prefer water molecules in this. Only ammonia will be there. So the ammonia is enter into the condenser here. We use some external cooling arrangement. So that we convert ammonia vapor into ammonia liquid. So there is a phase change. Temperature constant or phase change. So this ammonia liquid is entering into the expansion wall. So it is a restricted passage here. So what will happen? There is a huge pressure drop. So that ammonia high pressure liquid, so it will be converted into a low pressure liquid here. So pressure and temperature is directly proportional here. So what will happen? This ammonia will get cooled because it is allowed to pass through expansion wall. So there is a pressure drop, corresponding temperature drop will be there. So we get an immediate cooling effect here. Of this ammonia. So the cold ammonia in the liquid form, it is high pressure, it is low pressure. Cold ammonia in the liquid form, which will enter into the evaporator here. So whatever the load, we keep it here. For example, இங்க பாத்தீங்கன்னா sodium chloride brine solution, salt water அந்த மாதிரி எடுத்து they are cooling it, cool பண்றதுக்காக அனுப்புறாங்க. அந்த மாதிரி otherwise we keep whatever the load, we keep it here. So we can able to extract heat from this load. So we are providing a cooling effect here. Cooling effect இந்த இடத்துல கிடைக்குது ammonia liquid. There is no water molecules here. So cooling effect we achieve it here. So the cold ammonia liquid is entering here. So whatever the load, we keep it here, it will extract heat from that. So here again a phase change. So liquid ammonia is converted into a vapor ammonia. So that that vapor we are getting as a hot vapor here. Again it enters into the absorber here. Absorber la போகும்போது, so it gets mixed with the water. Okay. So இங்க பாத்தீங்கன்னா இங்க suction line heat exchanger இருக்கு இல்லையா, இந்த இடத்துல என்ன ஆகும்னா we have இந்த இடத்துல ammonia will be evaporated. Ammonia evaporate ஆனா இங்க water தான் இருக்கும் இல்லையா. Okay, water இருந்ததுன்னா we call it as a weak solution. More rich ammonia we call it as a strong solution. So if the ammonia is less means we call it as a weak solution. இந்த இடத்துல ammonia எல்லாம் evaporate ஆகி போயிடும். So we have only water. So that water is again sending back to the your absorber here. அப்ப போகும்போது என்ன ஆகும்னா, so here we have a heat exchanging process. So the heat will be transferred here. Okay. So because it will be a hot water, so the heat heat கம்மி ஆயிடும் heat exchanger. So that we preheat that here. So the amount of heat which is given here may be less. So that is the purpose of use heat exchanger here. So that water which is coming out from this heat exchanger, okay, so it is coming through passing through the reducing valve and is coming to the cooling water here. Okay, இது வந்து ஒரு நான் ரிட்டர்ன் வால்வ் டைப் மாதிரி. So it is again sending into the absorber here. So in this way the vapor absorption system is working. So if you closely observe this, some points we can get it from this. So what are all the points here? First point is in the case of, if you compare with the vapor compression vapor absorption system, so it consumes a lesser amount of power, because electricity in our lab we have a vapor absorption system, as I told, we are giving just less than 100 watts. Less than 100 watts is very very small amount, just equal to our tube lights, that's all. Okay, or one bulb 60 watts maximum நாங்க கொடுத்திருக்கோம். So it is very less. Even without electricity the system will run. Yeah, steam or hot water is just because ammonia boiling point is very less, quicker boil ஆயிடும். -30°C quicker boil, நம்ம boil மட்டும் பண்ண போறோம், ammonia evaporate பண்ணனும், அவ்வளவுதான். அதுக்கு வந்து small amount of it is sufficient. Okay, so another thing, if you see here, another point here you use your water use போது vapor don't have water, only refrigerant. Okay, this vapor absorption system, another drawback is we cannot use a system where we have less than 0 degrees. ஏன்னா water less than 0 degrees Celsius இங்க system operate ஆச்சுன்னா freeze ஆயிடும். Up to 0 we cannot use vapor absorption system, because water we are using wherever it goes woodல வந்து some small traces of water இருக்கு அப்படின்னா maybe 1 or 2% இருந்தா அது freeze ஆயிடும். So ice ஆகும்போது so it may clog the system will not work. அந்த மாதிரி below 0 conditionக்கு we cannot use it here. So vapor compression system, it can even work at -5°C, -10°C, because that is a different, because we don't have water there, refrigerant is there. Okay, refrigerant boiling point and freezing point is different than your water. So that is another thing that we can understand with respect to the vapor compression system and vapor absorption system. That is the major difference. Vapor compression system will consume more power, but it will give very high cooling effect and also in a faster manner. But vapor absorption system will absorb less power, but cooling effect is very low. We cannot go below 0. So that is a major difference between the vapor compression system and vapor absorption system. Where we use vapor absorption system, suppose for example commercial places irukkalama, commercial places la வந்து large area, இப்போ large area வந்து நான் vapor compression system போனோம் அப்படின்னா I need huge amount of power, compressor capacity, ton of refrigeration அதிகமாக வேணும். ஒரு பெரிய ஏரியால வந்து cooling effect moderate இருந்தா போதும், 5 degree 10 degree Celsiusல moderate இருந்தா போதும் அப்படின்னா I no need to go for a